Hello. In this video we will continue our look into how Newton's laws work. The logic in this second video will be considerably less involved than that in the first video, as this video concerns Newton's second law, which is quite easy if you understand the first law. Let's first briefly remind ourselves of Newton's three laws, which state that a body remains at rest or travelling at a constant speed unless acted upon by an external force. That the force acting on a body is equal to the rate of change of the body's momentum, and that every action has an equal and opposite reaction. In the first video, I dwelled at length on the first law. I argued that physics is our attempt to answer an ancient question on the nature of change. I further said that in physics we state that change happens when something external to a system acts upon it, and I said that when we use the word system, we mean by this a part of the universe. I then argued that our first step in developing any physical theory was to characterize the way the system behaves in the absence of an external agent. In Newtonian physics, this is done by asserting that a body remains at rest or travelling at a constant speed unless it is acted upon by an external force. Having explained how the system behaves in the absence of an external perturbation, we now want to explain how the system will behave when it is perturbed by some external force. This is the purpose of the second law. Remember, the second law says that the force acting on a body is equal to the rate of change of the body's momentum. We are thus explaining what effect an external perturbation, in this case a force, has on the behaviour of the system. Rather obviously, the system will behave in a way that is contrary to the way it behaves when no external agent perturbs its behaviour. Therefore, in Newtonian physics, the momentum of the body will change when an external force is applied, as this quantity does not change in the absence of a force. In more general terms, whenever an external agent perturbs the behaviour of a system, the state of the system will change. Newtonian physics is quantitative, and as such, Newton's second law gives a mathematical equality between two quantities. We are told that the force and the rate of change of the body's momentum are equal. We can write this equality as shown here. Within this equation, the momentum is written as a function of time, p of t. Remember, a function is a mathematical object that takes in an argument and that outputs something else. In this case, the argument of our function is the present time, and the function returns the system's momentum at that time. The numerator in the quotient shown on the right-hand side of this equation thus tells us how much the momentum changes during a time interval of length delta t. This is then divided by delta t. If we were to draw a curve that represents the p of t function, with t on the x-axis and p of t on the y-axis, as shown here, the quotient on the right-hand side of this equation would give us the gradient of the chord, shown in red in this figure. The numerator of this expression gives us the amount this linear function increases by, the rise of the linear function if you will, while the denominator delta t tells us the time interval during which this rise was observed, the run. The rise over the run of a linear function mx plus c is equal to the gradient m. Thus far we have neglected the limit sign in drawing our function and the chord. We can remedy this, however, by imagining how the gradient of the chord changes as the 2 points at which it touches the curves are brought progressively closer and closer together. Clearly, in the limit when delta t tends to 0, our chord changes to a tangent as it only touches the curve in one location. We know that the gradient of a tangent to the curve at any point is given by the derivative, and it should thus come to no surprise to us that the limit on the right-hand side of this equation is just the definition of the derivative. Let's quickly confirm that this limit is the definition of the derivative by an algebraic argument rather than a geometric one. Let's consider the function p of t equals t squared. Probably the first thing we learnt in calculus was that the derivative of this function, p of t equals t squared, with respect to t is equal to 2t. We can now prove this by solving the above limit. Notice first of all, however, that in the limit as delta t tends to 0, both the numerator and denominator of this expression are 0. When we are thus asked to solve this limit, we are being asked to evaluate 0 divided by 0, which can equal any number because 0 multiplied by any number is equal to 0. When we substitute p of t by t squares, we find that p of t plus delta t is simply t plus delta t all squared, while p of t is t squared. Expanding out the brackets, we arrive at a numerator of t squared plus 2t delta t plus delta t all squared minus t squared. The plus t squared and minus t squared terms in this expression cancel. In addition, we can cancel factors of delta t that appear in the numerator and denominator. This leaves us with the following limit to solve. The limit of 2t plus delta t as delta t tends to 0. Obviously, this is simply 2t. Let's finish by summarizing everything from these first two videos. I have argued that physics is our attempt to answer an ancient question on the nature of change. I further argued that in physics we state that change happens when something external to a system acts upon it. So for example, this system's momentum changes when it is pushed by the red bird. In Newtonian physics, an external agent applies a force, essentially a push or a pull, to the system, and this force causes the system's momentum to change. Lastly, the total change of momentum is quantifiable because the force acting on a system is equal to its rate of change of momentums. We express this mathematical sentiment in mathematical symbols using the equation shown at the top of this slide. Thank you for your attention.